Hello everyone, my name is Noor-e, and this is my lab 3, Black Hole and Orbits. There are two parts to this lab. The first part, we're going to analyze the motion of a star orbiting a black hole to estimate the black hole's mass, and in the second part, we're going to simulate the motion of a spaceship around a planet-moon system and determine the initial velocity needed to achieve a complex figure-8 shaped orbit. Part 1, finding the mass of the black hole. In this lab, we will use two fundamental formulas. The first is Newton's second law, which is F net is equal to ma, and the second is the formula for the gravitational force. So first, we calculated the velocities from each position using the positions from the computational model using v equals dr over dt. Then we used each velocity to calculate the acceleration using a equals acceleration equals dv over dt. And then we used the fundamental principle F net equals ma to get the net force on the star at each point. Then we substituted each net force into the left side and we rearranged the gravitational force equation to find the mass of the black hole. Since we had many different masses, we added all of those masses up and we calculated the average to find a single mass for the black hole. So this is the computational model that I used to calculate the mass of the black hole. Here we can see that I'm using the initial velocity given and final velocity given to find the initial final momentum by multiplying by the mass, and then I'm using dv over dt to find the net force, and then I'm using the parallel and perpendicular components to find the mass at each point. And then here I'm adding all the masses up and I'm dividing by the number of masses to get the average mass of the black hole. So here is the result that we have. As you can see, it orbits around fully, and then at the end we have the calculation of the average mass of the black hole. Part 2, achieving a complex orbit without crashing. In this part, we need to find the initial velocity needed to achieve a complex orbit influenced by both the moon and the planet. To start, I calculated the net forces on the moon and the ship at each point using the computational model, and we used both forces to predict the trajectories of both objects using the velocity and position update formula. My main strategy after then was to use trial and error and repeatedly just adjusting the velocity components so that I can achieve a stable complex orbit that demonstrates the three-body gravitational interactions between these three objects. And so I used 3 steps to mainly get that initial velocity. First, I used the moon's velocity as an initial baseline orbital speed. I then added extra energy to allow for a larger orbit around the planet, and then after that I added an X component so that it can be an 8 shape. So here is the computational model that I used. Here we can see that we're calculating the net forces. So this is the calculation for the net force on the moon. This is the calculation for the net force on the ship. And then here we're calculating the trajectories of both using, here is the trajectory of the moon using both the velocity and position update formula. And this is the trajectory of the ship using both the velocity and the update formula. And here at the end, you can see that this is what I set the initial velocity of the ship so that it can achieve a complex 8-figure orbit. So this is the result of my computational model. As you can see, it does a figure 8 loop because it's influenced by both the gravitational forces of the moon and the planet, which gives it a complex orbit. So some possible errors in my experiment include measurement and estimation errors, which could be due to inaccurate tracking of the star's position or orbital radius. And since we are using a simplified physics model, we are essentially ignoring other factors that could be affecting the orbit in outer space. And lastly, numerical and simulation limitations may introduce small errors from rounding and time step size or coding precision. So some further questions to ask is firstly, how are the net force and rate of change of momentum and their components different? Well, they're essentially the same thing, but describing different perspectives. The rate of change of momentum is what we measure directly from observing the star's change in velocity, and that is, according to Newton's second law, that is equal to net force, which means they're the same thing from different perspectives. And then we can divide the net force into parallel and perpendicular components. The parallel component changes the speed, perpendicular component changes the direction, and together they fully describe the black hole's the influence of the black hole. Secondly, what if you wanted to simulate the entire system, including the black hole, and what gravitational force would you include? Well, we would need to include all 6 gravitational interactions between every pair of objects, and in this system, each celestial body with more mass would dominate the one with less mass. And so the black hole would dominate the star's motion, the star, the planet, and then the planet would dominate the moon. But they will all have influence on each other, even if they're small. Thank you.